Welcome to a short presentation illustrating current results of the CIRIS project. CIRIS, Semantic Reflection for Real-Time Interactive Systems, develops alternative and novel approaches to software techniques and architectures for intelligent real-time interactive systems. Simulator X is the project's software technology testbed, with application areas in virtual, augmented, and mixed reality and computer games. The current release provides a scalable and concurrent architecture with an additional support for the integration of various artificial intelligence methods. Typical applications using this architecture are built around loosely coupled components. These components include rendering, physics, or AI, and various others that work together to create an interactive simulation. Components should effectively run in parallel, enabling the application to benefit from modern hardware capabilities. Simultaneously, it should be easy to exchange any component with minimal effort and side effects. Actors are universal primitives on concurrent computation. They represent independent flows of control communicating exclusively via messages. In response to a message that it receives, an actor can make local decisions, create more actors, send more messages, and determine how to respond to the next message received. A bootstrapping actor spawns component actors for services like rendering, physics, AI, and sound, for example. Scalability is an important aspect of our actor-based architecture. Concurrency is supported on multiple levels of resolution. Starting from the macro level of the components, any computational task can be parallelized easily from individual ghost behaviors to primitive animations. Hence, components may also use multiple actors internally. Here, a rendering component uses multiple actors to support multi-view setups. Scalable concurrency is extremely beneficial for AI components. For example, a single behavior actor can control groups of ghosts as well as individual entities. Even more, individual AI actors are free to spawn additional actors for time-consuming tasks like path planning and others, which must not block the current behavior. The utilized actor model of Simulator X provides concurrency on different levels of granularity using a uniform and consistent concurrency paradigm and communication interface. At runtime, components may create, modify, or remove entities in the virtual worlds. As communication is solely achieved by message passing, a mechanism to obtain a coherent global state is needed. The current architecture uses entities as collections of properties, each implemented using so-called state variables. State variables are created and owned by one, but are accessible to all participating actors. The owner manages data storage as well as access requests. For example, a successful write request by one actor will automatically send value change messages to respective observers. Simulator X uses the underlying actor model to provide the illusion of a consistently shared mutable global state made up of entities. For example, a physics engine modifies the transformation property of a barrel using a state variable. A graphics engine observes this variable to render the barrel at the correct location. Additional properties can be added to represent further aspects, each modified by individual components and actors, from primitive animations to elaborated AI behaviors. Properties, represented by state variables, are grounded into an ontology. This ontology provides a facility for unique identification and semantic word representation. The first is highly beneficial in terms of exchangeability and interplay of components, since it decouples individual naming schemes and representations. The second is of particular value for several AI methods. For example, it is a requirement for multimodal speech and gesture interfaces as well as for the incorporation of autonomous intelligent agents. Several demo applications were developed to demonstrate the usefulness and adequacy of the architecture and to provide some coarse high-level performance cues. The applications already combine physics simulation, high-quality renderings, behavior simulation, as well as multimodal gesture and speech interactions in game scenarios using immersive displays. Simulator X's current architecture provides a unified and scalable concurrent programming paradigm for intelligent interactive applications. It is portable to all major desktop and many mobile computing platforms. The use of the Scalar language incorporates modern functional language constructs, while its object-oriented concepts have been highly beneficial during the developer's learning phase.
flame.